not everything is understood. Yeah, so that sphere is non-conducting. I mean, the spherical shell surrounded, which formed by these spheres. Yeah, so it is non-conducting. So charge is spread. So that's what makes the problem a little bit more complicated, maybe. Charge is sitting inside of that shell, in the thickness of that shell. So we know that inside there is no charge. So we can assume that the field would be zero. Outside no charge also, but we know that some charge is included in any Gaussian surface which will make around that shell. So you keep it in mind. So our data would look like that. We show this non-conducting spherical shell, uniform charge density, because it might be not, it might be some increments of different material or whatever. But here, fortunately, uniform charge density. And we have three areas of interest, R smaller than R1, then our R between R1 and R2, and our R is larger than R2. So we want to find field in each of those areas, and it is good to write equation like this, so we know what field we are looking for. So we start from the inside part of the shell. So condition R smaller than R1, and always when you write, you need to specify A, B, C, what steps you're going through. We write that no charge here, and we write our Gaussian, we write Gauss law for this particular case. On the right side you see 0 because no charges inside of the R1 sphere with the radius R1. So if you take any Gaussian surface of any radius which is smaller than R1, there would be no charges inside. So that's what is used, R smaller than R1. So that is condition R smaller than R1 to choose our Gaussian surface. We remember that Gaussian surface, it is surface which exists only in our mind. It does not exist. We just show it. It is imaginary surface for purposes of just analyzing that problem. So we could write, we could show this radius will maybe smaller, maybe larger, but not larger than R1. We want something smaller than R1. Even we cannot take R small equals R1. So here our Gauss law again, on the right side 0, from which we immediately have that EA should be 0, because area does not equal 0, right? If any radius not equal 0, so area has some value, so field should be 0. And that's all our first one. Now a little bit more complicated inside of the shell itself. So between inner radius and outer radius. What makes it a little bit complicated is because we need to find what charge would be inside of certain Gaussian imaginary again surface, how much charge is sitting there, because charges spread uniformly. Smaller radius you take, still between R1 and R2, capital, I mean, smaller radius you have, less charge, right? If you get closer to R2, more and more charge will be enclosed. So we keep that in mind. And the formula to find charge Q net. So it means net charge which is enclosed in that particular Gaussian surface that are small can vary, but limits R1 and R2. Larger than R1 and smaller than R2. To apply our theorem, let me, well, actually, it would be a formula for Gauss theorem. On the right side, Q enclosed over epsilon 0. So we need to find that Q enclosed, or here it is denoted Q near. Obviously, it would be a charge density rho multiplied by volume, which is enclosed by that particular Gaussian surface. So volume of the sphere 4/3 pi r cubed, we know, but because inside it would be that empty sphere, so we need to subtract that volume of the small sphere inside, right? So that is our volume. And B I wrote here just for part B, let's say. VB, yeah. So as soon as you know volume, we can find Q net. So we multiply by rho. That expression. We can find now EB, because we know that EB, so it means field inside of that second area between R1 and R2 on any Gaussian surface which you choose would be the same. And notation for that field would be EB. So you can pull it out of integral. So on the right side, Q net over epsilon 0, and we divide over area of that particular Gaussian surface, which is denoted here AB. So AB, it is nothing else, our AB, it is area over dA with that particular area corresponding to that particular radius. So you need to keep in mind that here our R1, here our R2, and you see we could choose, maybe I want to choose this Gaussian surface radius R. But maybe someone wants to choose a little bit larger, right? Still, condition is satisfied. So to distinguish between those, let me write that as R1, R small 1, R small 2. But all of those R's, they're inside of our conditions between R1 and R2 capitals. Now in the area we compute, so our AB would be 4 pi R squared, depending on which radius you take, or R1 or R2. So that's whatever we want, radius, any, but between those R1 and R2 capitals. Okay. So charge we know, thus you can substitute here. You see here AB is 4 pi R squared. Substituted here. And after some cancellation of some factors, we are left with that formula which is underlined twice here. You see. Last case, when R larger than R2. If you would know total charge, you would write just Q over 4 pi R squared, and that's it, solution of the problem. But we don't know, we need to find the total net charge. So we need to find the volume occupied by the shell. So difference of volumes of two spheres, you see. Net charge, then you multiply just by charge density. And with that, you can find the EC. So field in the area C. Last question. And that would be the answer. And of course, here it could be done in more steps. You might do them at home, so you could write Gauss theorem in this form and write Q enclosed in this Q net equals all Z, and Y is all Z, so it is rho by V, and our V is Z with this, and actually here it is written. So that solves our problem.